Here's an example that elaborates a bit more on the typical way that structure objects are thrown around a program. We've already seen that we can pass structure objects into functions and that we can pass pointers to them, but I wanted to show off a typical example of a non-trivial case of a program that uses a few functions working with structures to show off some of the other things that we can do with structures that we can do with other variables that might not be obvious at first. And there are some aspects of this example that, if they confuse you a bit, I'm not going to use a diagram and do a full trace of them, but using a diagram and tracing through it might help answer any questions you have about the way the code runs. If you try running it yourself and it's a bit odd what it does, try tracing it now, because in this program there are a few examples of things that some people often have a bit of difficulty with at first, and it's good to take care of those issues as early as possible. So here's, I've got this structure type called point2D, and it stores a point in space, in 2D space, so float x, float y. Here is a function, I've renamed it, it's not just length anymore, vector length, to make it clear what I want is the norm of the point in space, so the distance from the origin. And this is assignment 4 review, so I won't belabor it too much. It takes a point as its argument, and it computes the norm of the distance from that point to the origin. Notice that it is taking a copy of the point, even though it's not modifying it. And the general practice is, if your object is pretty big, so bigger than 2 floats, you might want to pass it in with a pointer to avoid making a copy. But it turns out the computer does not have any trouble making a copy of a small amount of data, and it actually might be faster because of the way the way the compiler tends to treat these things. So we shouldn't sweat it if we're working with structs that are relatively small. If you have a structure type that contains arrays of maybe 1,000 elements or more, you might want to consider always passing them as a pointer as opposed to passing a copy. Here's an example. I want to add 2 points together. Here's an example of a case where a function returns a point object, which is completely valid. I can return an int or a float. Why can't I return a structure containing multiple things? When I return something, I am, of course, returning a copy. So I create my result object inside the function. I want to add together the points the same way I would add vectors in any other context. So I create a new point object. I set the x coordinate to be the sum of the x coordinates of the inputs, same for the y coordinate, and then I return that point object. And so what gets sent back to the caller would be a full point object, and then that gets copied into whatever the caller presumably uses that for something. Here I'm creating a point object to refer to the origin. Here's a function that just gives me a point object corresponding to 0, 0. So what this does, it takes no arguments and returns a point object. And you might be wondering, why would I bother doing this? Why not just create the origin yourself? And it's because it might be that the structure of a point object changes over time, and having a function to do it makes it more convenient. It also makes it more obvious when you're writing your code that you want the origin, that maybe there's something significant to that. But mostly it's a contrived example of a function that takes no arguments but returns a point. And then here's one we'll come back to in a minute. So here's a function we want to write ourselves. It takes a point, modifies that point in place. It doesn't return anything. It modifies the point to normalize it, which is where we determine the length of the vector and then divide both coordinates by that. Okay, so we'll come back to that. Let's take a look at main. So I create 4 points. There's P1, there's P2. P3 is the result of the origin function, so we expect P3 to be 0, 0. And then P4 is what I get if I add together P1 and P2. And the key thing here is that obviously I expect P4 will be the value 2, 1. So P1 plus P2 is 2, 1. But notice how P4 is being initialized to the result of calling a function and taking its return value. Okay, so I actually want to comment this out because I don't want to get ahead of ourselves here. What's happening in part B is something that causes people a lot of trouble at first because they want to identify what structure types do with what arrays would do. So let's start by taking a look at part A. Let's just verify that we've got the basics of that. There we go. I'm using the -lm flag because I'm using the square root function in this code. Okay, so part A. P1 is 1, 0. Yep, no surprises there. Its length is 1. That doesn't surprise us. P2 is 1, 1. The length of P2 would be the square root of 2, which is 1.41 and some other digits. P3 is the origin, and P4 is 2, 1, and I guess for what it's worth, that's its length. Okay, so then let's take a look at part B. I have this assignment statement. So there are lots of operators that don't work for structure types. and maybe we'll talk about some of those in a minute. One operator you can use on a full structure object is the equal sign, the assignment operator. You can also, as we've seen already, of course, I can work with members of a structure however I want. I can make pointers to them, I can add numbers to them, whatever, if their types allow that. But I am also allowed to make complete copies of a structure type. What this is saying on line 66 is copy all of P1 into P2. Set P2 to be a complete copy of P1. But the operative word there is copy. I'm not saying P2 and P1 are now exactly the same thing forever. I'm just saying take what's in P1, dump it into P2. If I go and modify P1 later, P1 is an independent object. P1 and P2 aren't always going to be equal. So if I use this assignment, I'm not saying that P2 is constrained to always be the same as P1. So let's demonstrate that. I'm going to set P2 to be a copy of P1, then I'm going to modify P1. So they should be different when I'm done. So we'll try that out. Okay, so I first set P2 to be a copy of P1. When I eventually print out P2, yep, there it is. It is a copy of the value that used to be in P1. And then I set P1, the Y member of P1 to be -1. And when I print out P1, yep, there it is. And P1 and P2 emphatically are different. That's significant because all this operator is doing is making a copy. Now, while we're on the subject, what operators can't I use? Okay, how about this? P3 equals P1 plus P2. And you might go looking at P1 and P2 and think, yeah, wait, a point is just a bunch of numbers. If I try and add two point objects together, wouldn't that just, default to adding together their members? Well, you'd like that, but no. Instead, the compiler says, I don't know what you mean. How do I add two of these containers full of members together? That doesn't make any sense. So you can't do this. You can't use this operator. And you can't use plus plus and you can't use plus equals. It would be valid to say something like p3.x equals p1.x plus p2.x because all of these individual things, p3.x is a float, p1.x is a float, p2.x is a float. We can do that arithmetic with floats. We just can't do it with the whole structure at once. And similarly, you might want to be able to ask questions like, hey, is P1 less than P2? Maybe that has some kind of a meaning. But it shouldn't surprise you to learn that, nope, you can't. The compiler doesn't know what that means. The compiler's not going to take a guess. What about equals? What about comparison equals? And it turns out even then the compiler refuses to let you do this. Even if you think, well, of course, just ask if all the members are equal to each other. There are a bunch of caveats there that the compiler doesn't want to resolve for you. For example, what if the structure contains an array and you ask if the arrays are equal? And the arrays are containing strings or something? Who knows? So the compiler says, none of my business. If you want to compare these two structures, you do it your damn self. You write a loop, you write a function, but you don't ask me to do it for you. So we can use the single equals operator on structure types, but that's pretty much it. We can make pointers to them, but we can't do too much else. Everything else we have to do by hand. If we want to compare all the members, we have to compare each member individually. We can't expect the compiler to do it for us. Okay, so let's try writing the normalize function. So the normalize function is to take a pointer to one of these point objects, and then to divide each coordinate of the point by the length, by the associated vector length of that point object. So we are going to need to get the length. So let's start with that, not int. Float length equals, well, we have a function that'll do it for us, vector length of what? Well, the vector length function takes a point as its argument. What I have here is a pointer to a point. So maybe what I want to do, I mean, you could do this by trial and error. If you tried passing in the pointer, the compiler wouldn't like it. Instead, I'm going to pass in the thing that it points to, the point object itself. And as I said earlier, sketching out a quick diagram can really help to justify this for you. So I'll try compiling that. Of course, I'm not done yet, but at least it's not giving a compile error on this line. So I get the length of this particular point object, and then what I want to do is I want to go in and I want to modify each of the coordinates to divide them by that length, to normalize the vector, to make it a unit vector. So here, I'm going to use the arrow operator. I'm going to take each coordinate pt arrow x, because pt is a pointer to a point object. And maybe that we could sketch a quick diagram of that. So here's my variable pt. It is a point 2D star. And it points at something somewhere, we don't really care where this thing is, something somewhere with an x coordinate and a y coordinate of type point 2D. But all I know about in my local scope is this. So this is my normalize function. Okay, so I would like to first get the length, which means I want to pass into my vector length function this, so I first follow the arrow, and then I want to normalize the coordinates. So the x coordinate, follow the arrow, get me the member called x. That equals whatever the current value of x is divided by the length. And then pt arrow y equals... Now, we could also write, remember that, of course, it's up to you, but you could also do this in the long form way using the star and the dot. So I could write star pt dot x divided by length, and then the y coordinate equals star pt dot y divided by length. That's also valid, but over time, I think the arrow operator will grow on you. It does make it way easier and easier to read, certainly, to work with pointers to structure types. Okay, so I have this. One thing I should observe is if I were doing this on an assignment or an exam, I suppose for the sake of demonstrating structures, this does the trick. We probably do want to put in a check to see if the vector is a zero vector, because we can't divide by zero. But we'll leave that for now for the sake of the simple example we're trying to do. All right, and so here, once I've normalized my vector p1, it ends up being 0.7, negative 0.7, fair enough. But notice how when I get its length, the length is 1.0. And that is the telltale sign of having a normalized vector if its length is 1.0.